Compare routing concepts of EIGRP and OSPF, advanced distance vector versus link state, load balancing, path selection, path operations, metrics. So in this table, it is summarized the difference between both protocols, the type of protocols, if they support BLSM, if they are classless or not. Remember that EIGRP can become classful if you enter the command auto summary. EIGRP is a proprietary CISCO protocol that has released an RFC to see how it works, whereas OSPF has always been a standard multi-vendor protocol defined in several RFCs. How the protocols see the network, how fast they offer you the convergence time, how they update information, what are the hello times for EIGRP, and the dead timer is known as hold time, and for OSPF, the dead timer is usually 4 times the hello time and has a wait timer that is used only for DR and BDR selection. Remember that equal load balance means using several paths that offer you the same metric to a destination. If you allow that, you can load balance packets sent to the same destination across different paths. EIGRP supports an equal load balance. That means that you can use several paths that have actually different metric to reach a destination. They will be used only if they abide by the formula, the feasible distance, the feasible successor feasible distance by the successor route feasible distance is less than the variance. They have different protocol, IP protocols numbers, and different multicasts. If you configure EIGRP, you must remember that you can run multiple EIGRP processes in the same router, but the number that you use is the autonomous number. That is significant. It is important because that number is sent over the wire, whereas OSPF uses process numbers that are locally significant. The number that you choose at each router is not really important. And those are your packets for your EIGRP, hello, request, update, query, and reply. OSPF uses hello, database description, link state request, link state update, and link state acknowledge. Regarding summarization, you can summarize with EIGRP at any router at any interface, whereas in OSPF you can only summarize at the AVRs, which are the routers that separate areas. In EIGRP, two routers can become neighbors if they have the same autonomous system, the same key values, and the same authentication type, and if any, the authentication must be successful. Whereas in OSPF, in order for two routers to become neighbors, they have to have different router IDs. They must be unique, share the same subnet, have the same MTU, area ID, area flags, DR settings, and the authentication method must match, and if any, it must be successful. The topology table for EIGRP is only a list of prefixes or destinations, and for each prefix you will have the feasible distance, the metric, the successor, the next hop, the interface, the outgoing interface, and if any, a list of feasible successors, a list of possible alternate paths to the same destination. So for each feasible successor, you will have a reported distance, the metric that will be calculated from the point of view of your neighbor, or the feasible distance, that is the metric calculated at the local router. Whereas in OSPF, what you will see if you see the topology table is all your LSAs. You can have LSAs 1, 2 through 7. LSA 1 are created by any router. LSA 2 are created by any DR router. LSA3 are created by ABR routers, and so on. So how EIGRP achieves path selection? EIGRP will calculate the feasible distance, the reported distance, and feasible successors in order to locate loop-free paths. It will use split horizon and Poisson reverse as protection, and it can have alternate paths to a destination known as feasible successors that can become feasible successors only if they abide by this condition. The reported distance is lower than the feasible distance. Whereas the path selection in OSPF is made by running the Dijkstra algorithm. This algorithm will provide you with loop-free paths. In order to run it, its router places itself as the root of a tree. If several paths exist for the same destination, the one that has the lowest cost is preferred. If there are several paths having the same cost, equal load balances can be used. What happens if you have a change in the network? For instance, what happens if the next hop for a destination is lost? So in that case, EIGRP will do the following. It will try to use a feasible successor, which is an alternate next hop. So if a feasible successor does not exist in the topology table, the route will become active, and dual kicks in. Dual is a mechanism that will send queries to all downstream routers asking for a feasible successor for a successor for a route. That means it will ask for routers if they know an alternate path to the missing destination. So these other routers can only do one of two things. They either reply with "I know" an alternate path, or they will send this query downstream again. So this query will travel all your way, all across your EIGRP networks until that query finds a query boundary, which is a filtering point, a summarization point, and a stop router, or a router that has a different autonomous system. And that router that lies at the boundary can only do two things, saying, I don't know anything, or I know an alternate path. So replies should get sent across all your EIGRP network to the router that is asking. So if not all replies to all queries that were sent are received, the route becomes stuck inactive. Otherwise, if a successor is found, the route becomes passive again. And this is a very complex process. Whereas in OSPF, what happens if a topology change occurs is just run Dijkstra again. You might receive an updated LSA. When something happens, you will update your leak state database, and you have to run Dijkstra again. Remember that these LSAs have a sequencing number, so if you receive a LSA that has an old sequence number, you will ignore it. LSAs also have an aging time, which is 30 minutes. And if an LSA within your database reaches 1 hour, you will have to erase it from it. So the metrics, EIGRP metric is a whole formula with K values, and it's multiplied by 256. Most of these K values must be 0, but if you look at the formula, you will know that it is incorrect, because if K5 becomes 0, the whole calculation becomes 0. So ignore that part and think that if K5 is 0, that part does not exist in the formula. And usually K2 and K3 will be 1, and you will be dividing 10 to the 7 power by the minimum bandwidth in your pad, and you will have to add the total delay by 10, and the result will have to be multiplied by 256, and that's it. If you want to change the delay in an interface, remember that you will be giving this number in tens of microseconds. So if you enter delay 9, you will be actually telling the router that this interface has a delay of 90 milliseconds. You may also change the bandwidth, but you should not, because the bandwidth must reflect the real bandwidth. Otherwise, you might impact other protocols. If you have interfaces that go beyond the 10 gigabit per second rate, you should use the white metric that uses that formula. In this case, the delay is in picoseconds, and whereas in OSPF, the cost of each interface is calculated by dividing the reference bandwidth by the bandwidth. You can change the reference bandwidth, but you should do it in all your routers. You can also change your cost directly in the interface with the IP OSPF cost command. That's it.